Hello, everyone. Welcome to our next unit, but it does fall in the entire um, topic of advanced chemical ratios. Now we're going to look at chemical compositions. So, looking at different ways to write or figure out slash determine out formulas. So, these notes are N29, percent composition, and empirical formulas. As usual, well, not usual, it's been a while, but here let's make sure we write down our target this time. I can calculate percent composition and empirical formulas for various compounds. Take a moment and write that one down. Alrighty then, moving on. So, percent composition, determining how much of a molecule's mass is from each element. So, ultimately, it looks just like a fraction. It's the part over the whole times 100 equaling a percent. We're all familiar with this when it comes to assignments. What score did you get over the possible total score? For our purposes, we just take the element's mass we are focusing on and divide that by the molecule's mass times 100 gives us our percent composition. Pretty straightforward. As long as you have a periodic table, you guys can do molar mass. It's pretty simple in that respect. So, a few things to do. Find the molar mass of the entire molecule. Again, we've done that. Nothing new there. And then just divide each element's atomic mass by the molar mass of the molecule, kind of like we just saw in the previous slide. Multiply by 100 to put your answer in terms of an actual percentage. Can't forget that multiplying by 100. Quick note, if you add up the percents for each element, it should add up to 100%. That makes sense. But rounding answers may make it not quite add up to 100. That's okay. Again, please make sure you use the full molar mass as written on the periodic table for this class. Do not round molar masses. Let's all be aware of that one again. Do not round molar masses on the periodic table. All right, so for example, let's calculate the percent composition of each element in magnesium carbonate. Got to know your ions. You got to be able to write a formula so you can actually do this. So, reminder, percent composition is just element's mass over molecule mass. So, we look at magnesium carbonate, and we can add it up. Is the formula Mg CO3. As we can see, 1 magnesium at 2431, 1 carbon 12.01, and there are 3 oxygens, each at 16 apiece. All right, easy enough. So here's magnesium, here's carbon, and lastly, oxygen. But please notice I did not put 16 in this equation for finding the percent composition of oxygen. There are 3 oxygens in the molecule. So again, if there are more than one of an element and you're finding the percent composition of that element, you have to multiply by subscripts to get the total of that element within the molecule. And add it up, it equals 100. Any questions on this one? Okay. All right. Next step, empirical formulas. They are the simplest reduced version of a formula. Smallest whole number ratios possible, meaning the subscripts are lowest terms. A molecular formula is the real version of the formula. May or may not be in the simplest, most reduced form. It just depends on that formula. So empirical is always simplest reduced. Molecular is just a multiplier of the empirical. So, a couple examples. If we look at C6H6, I can reduce this down to just CH. So the ratio holds true. Empirical lowest terms, molecular is, again, a multiplier of it. Questions on this? Okay. Now, keep in mind, when we talk about ionic formulas, ionic compounds, they are always empirical from the very get-go. You don't reduce them because they're already reduced to the lowest terms anyway. So ionic, they're already done the minute you write a compound, crisscrossing the charges. Yes, obviously we got to make sure they are lowest terms, but once you've written your compound, that is your lowest terms. Covalent formulas, as we just kind of saw in the previous slide with carbon and hydrogen, sometimes empirical, sometimes not. So a few more examples. Here's water, H2O. It's still H2O. Can't reduce that one. Here is C6H12O6. We're all familiar with this one in glucose, blood sugar. That can be reduced or divided out by 6CH2O. And then C12H22O11, again, cannot be reduced. So you can see as sometimes they can and sometimes they cannot be both empirical and molecular. Questions on this one? Alrighty then. So how do we determine the empirical formula? We have a few things we have to go through. Well, usually you're going to be given the percent composition to start. We're going to assume a 100-gram sample. It just makes the numbers easier. So you're not going to be told how large your sample is, but it's just a rule of thumb, assume a 100-gram sample. Then we use the rhyme. This is a very great rhyme. I love this one. You ready for it? Here goes. Percent to mass, mass to mole, divide by small, multiply till whole. It's a great rhyme. You need to memorize this rhyme. Percent to mass, mass to moles, divide by small, multiply till whole. Some may call it a poem. I've always called it a rhyme. Yeah, tomato, tomato. You pick which one you want to call it. Well, let's do an example together. All right, so here we are. A diptic acid has these percentages by mass. What is the empirical formula of a diptic acid? All right, so percent to mass, step one, just convert your percentages to grams. Easy enough. You erase the percent sign and change it into a G. That's literally it. Mass to mole, well, that's just converting from mass to mole using molar mass. Nothing new there. You guys have all done this before. So I'll take carbon divided by its molar mass. I'll take hydrogen divided by its molar mass. And lastly, I'll take oxygen divided by its molar mass. Simple enough. Any questions on these first two steps? Alrighty then. So, number 3, divide by small. Basically says we're going to divide the mole values that we just determined by the smallest mole value found. The goal of this one is to get you to the simplest ratio. So we'll take carbon, hydrogen, and oxygen. Our carbon mole number was this, hydrogen and oxygen. Notice the smallest number was oxygen, so I'm going to divide by 2.74 for all of them, and I get my simplest ratio. Questions on what I did here? Alrighty then. Now, multiply till whole. This is not an always happening step. For our example right now, it is going to happen, but not always. Now, multiply the values found until they are whole numbers. The numbers may not be perfect. You might have to round a little bit. That's fine. But you have to multiply them all by the same number. That's the most important part. So we saw that carbon was 1.5, hydrogen was 2.47. Well, we'll call that 2.5. And we know that oxygen was 1. So easiest way to get to a whole number is just multiply everything by 2. Because if I do that one, and then that one by 2, and then that one by 2, Again, they all have to be multiplied by the same number. I get 3, I get 5, I get 2. Pretty straightforward in that sense. Therefore, when I take these whole numbers as my subscripts, I get my empirical formula for a diptic acid. Any questions? All right, so something to add. The numbers are not going to come out always perfect. There's no set range on when you should multiply till whole or you should just round. I can be for certain if you're plus or minus 0.1, you're just going to round to the whole number. Obviously, right here in the middle, 0.5, you're going to multiply till whole. If you're a 0.3 or a 0.75, you're probably going to multiply till whole. There's a little bit of a gray area between 0.75 and 0.9. It's just you got to play with it and kind of see what makes sense if you come across those examples. Now, we have our empirical formula. Now we need to figure out the molecular formula. Okay? So we find the molar mass of the empirical formula. Well, you just found the empirical formula, so you can use the periodic table. Then we're just going to divide the molecular formula mass by the empirical formula mass. You have to be given the molecular formula mass as part of the problem. Makes life easy. You're given one number, you find the empirical formula, and you divide by it, and will give you a factor. Once you take this factor or multiplier, you're going to multiply your empirical formula subscripts by this multiplier found from your empirical formula. Easy enough. Unfortunately, no cute rhyme this time. I'm sorry. But, don't forget the rhyme. Percent to mass, mass to mole, divide by small, multiply till whole. So, the empirical formula for a diptic acid we found to be C3H5O2. The molecular mass of a diptic acid is 146 grams per mole. What is the molecular formula of a diptic acid? Well, here's my empirical formula mass. Easy enough. Periodic table. Find your molar mass. Now we're just going to divide by the empirical formula. So, molecular mass 146, empirical mass 73.08. I get 1.997, round that to 2. Again, you might have to round a bit on this one almost every time. Well, now let's multiply the empirical formula by this multiplier that we found in step 2 above. And there we have our molecular formula of a diptic acid. So a diptic acid has an empirical formula that is half of its molecular in this situation. And then now the problem is done. Any questions on empirical formulas? Okay, we be done. Thank you very much. See you next time.